Hello, BTC Bash. My name is Joey Yandle. I'm a cryptographer working for Trust Machines. And today we're going to be talking about Frost and how it works. So, first question is, what is Frost? Frost is a protocol that allows a number of parties to create a shared key. And then a subset of these parties, a threshold of them in fact, can then sign messages with that key. So what does Frost stand for? It stands for flexible, round optimized, Schnorr threshold. So let's go into each of these one by one. Flexible. Frost can work in many different configurations with various trade-offs. These include with or without centralized coordination, and the option to batch certain elements of the signing protocol. Round optimized. Frost is optimized for the case where there are no malicious actors present. This is unusual in these kind of protocols. Most of these protocols try to optimize for being robust in the case of malicious or non-participation. Frost doesn't do that. Frost optimizes for the case where there are no malicious actors and where everybody's participating fully. This is a good choice for cryptocurrencies because you can detect malicious actors and remove them and possibly sanction them in terms of slashing their money or their rewards. And once removed, the protocol can continue. And this is why we choose to do this in Frost and why we choose to apply Frost in a cryptocurrency context. Schnorr. Frost produces a Schnorr proof. Schnorr proofs are one of the old early zero-knowledge proofs, and they can be now, as of the Taproot upgrade, be verified on Bitcoin. Schnorr proofs can also be aggregated and verified in batches for high performance. This is very important in a cryptocurrency context. Threshold. Threshold signatures, they allow a subset of possible signers to produce a valid signature. Classic threshold signatures like M of N multisig require separate signatures from each signers. But more advanced threshold signatures, like Frost, are aggregated, so they take up less space. They also hide who were the people who actually took part in making the signature. So what do we need to do? What are the protocol requirements in order to run Frost? Well, we need the number of parties in, and we need the threshold required to sign T. These are very important because these are used in the mathematics that help us create the distributed keys. When these distributed keys are also mathematically encoded with these numbers, which is how the signatures are only valid if a threshold signs. Each party in the protocol is assigned an identifier between 1 and n. Each party also generates a private key. Now, this is kind of orthogonal to the protocol itself, how we choose to sign messages, but we're going to have to send messages from different protocol participants to others, and we need to be able to verify that these messages came from the people who they're supposedly coming from. In order to verify this, we also have to register the corresponding public keys to our private key so that we can do these verifications. We also need some kind of encryption method because some of the protocol elements require that we send things privately between one party and another. Again, this is orthogonal to Frost itself, but it's necessary in order to run Frost correctly. So next we need to talk about Lagrange interpolation. Lagrange interpolation is a mathematical technique that allows us to uniquely determine a polynomial from a certain set of points. So how many points we need to uniquely determine a polynomial? Well, if it's degree n, we need n plus 1 points because a polynomial of degree n has n plus 1 parameters. Now, we could use linear algebra to solve this problem, but using linear algebra to solve this problem doesn't let us actually use this kind of technique in a closed form to build protocols on top of it. But Lagrange interpolation does. So it provides the closed form, which allows us to build a protocol like Frost with its distributed key generation and its signing on top. And so we don't actually really want to interpolate these polynomials when we're doing Frost. What we actually want to do is we want to interpolate the constant factor. So let's go and let's see what we're talking about here next. So another thing is Frost has the option, as we told us, Frost is a flexible protocol, has the option of using a semi-trusted signature aggregator. This entity can be one of the parties, or it can be a completely unrelated entity. The aggregator doesn't gain any special knowledge. They're only trusted to send out signing requests and combine the responses. Now, we don't actually have to have a signature aggregator. We could just have everybody view the messages. Anyone could submit signing requests, and everyone could, for themselves, aggregate the signatures and come to their own conclusions. But it's more efficient, especially in a cryptocurrency context, to have someone coordinate these kind of activities. So the first thing we have to do once we have our protocol parameters, and once we know the protocol and we've written our code, is we have to run a distributed key generation. What we have to do for this is each party creates a private polynomial f. So first of all, let me talk for a second about the mathematics here. So whenever we're doing cryptocurrencies, especially if we're doing Bitcoin kind of things, we're always using mathematical groups that are called elliptic curves. We don't do this because we have any particular fondness for elliptic curves. We just do it because we can have the same security parameters with much smaller key sizes. So when we see these polynomials, these lowercase elements here, these are curve point scalars. These are just big numbers, modulo some large prime. The big numbers here, these are actual curve points themselves. So each party first creates their private polynomial, where each of the parameters is a scalar which functions as a private key. So as we can see here, for a t-1 degree polynomial, we have t parameters from 0 to t-1. This is why we need t people to interpolate, or t points on the curve of polynomial to interpolate. So the parties then create the corresponding public polynomial by multiplying each of these scalars, each of these private coefficients, by the curve point generator. So now each party has a private polynomial, and now they have a corresponding public polynomial. So what do we do once we have these polynomials? Well, first of all parties distribute their public polynomials to all the other parties. We call these public shares for short. Then all parties take their private polynomials, and then we evaluate them. We evaluate them at every single party's ID. Remember, I said one of the protocol parameters for Frost was each party has to have an ID between 1 and n. So we evaluate the private polynomials at every party's ID, and then we encrypt them separately to that party and then distribute them. Now, what we're probably going to do most of the time is we'll create one giant private share, just like we'll have a public share, but each of the individual polynomial evaluations will be encrypted separately to the desired recipient. And then we distribute both the public and the private shares. So what happens when you receive the private shares and the public shares? Well, the first thing you're going to want to do is decrypt your private share. And then you check them against the sender's public polynomial. If you recall, I said that the public polynomial is just the private polynomial multiplied by the curve point generator. This means that the polynomial evaluation is also just the value. The public evaluation is just the private evaluation also times the curve point generator. We use this as a check to make sure that we were sent a valid share without ever having to actually reveal the private polynomial of any party to any other. So if we get all of the shares, and if they are all valid, we add them all together. What this does is, the way that Frost is going to work is all of these private polynomials are going to be added together to form a group polynomial. But no one's ever going to see this group polynomial. It's only going to exist ephemerally, and we're only going to send out these tiny little pieces of them and then combine them. And this is the first time we do that. We combine all of the valuations for our ID from all of the private polynomials of all the other parties, and we add them together. What this does is it gives us a point on this group private polynomial that no one ever sees. This is what we call a secret share or a key share, and it's what we're going to use to actually make signatures. Secret shares represent a point on the group private polynomial. Let's say that again because it's not obvious when you read the paper. This is what's really going on. So at this point now, we have finished distributed key generation, and we have a public key and a private key for the entire group. Like I said, the group will have a private polynomial, which is just the sum of all of the individual party polynomials. And this polynomial has a constant factor. It's the factor that doesn't have an x in it raised to any power. And remember what I told you that we were going to, when we were doing Lagrange interpolation, where we're actually never going to interpolate these polynomials. We're actually just going to interpolate this constant factor. So this constant factor is what actually functions as our group private key. So now that we have a group private key and a group public key, how are we going to sign? Well, the first thing we have to do before we sign is we have to generate a nonce. A nonce is a number used once. In Frost, our nonces consist of a pair of nonces, D and E, with a corresponding public nonce. And like everything else, when we're dealing with curve points or any kind of group theory, the public will always be the private times the group generator. Parties will distribute the public nonce and keep their private nonce hidden and secret. So remember before when I said that Frost is a flexible protocol. This is another place in which Frost's flexibility shines. The nonces can be generated in advance or on demand. This is necessary, or this is possible, because the nonces aren't actually related to any of the actual messages that are being generated here, or to any of the messages that are being signed. So we could, if we wanted to have our protocol execute more quickly, we could generate a large number of these nonces in advance and store them somewhere. But this is a trade-off, like all things in life. If we generate a bunch of nonces in advance and store them, then we can run the protocol faster. But we have to store them, and we have to keep them stored, and we have to have everybody seeing the same view of this storage. So these are our options, and these are the trade-offs that they have. So now that we have nonces, how do we create actual signature shares? How do the parties make their individual part of the group signature? Well, first of all, we have to select a set of the parties and their nonces. And this set has to be at least of size t, the threshold. Remember, because the polynomials have t parameters to them, so in order to interpolate the constant factor of the private polynomial, we need at least t parties. We can have more. We can have all n parties if we want, but we need to know in advance which ones we are actually using. So once we've selected our set S, our signing set, we create the binding value row. What row does is it fixes the signature to the message being signed, the full set of public nonces, and the individual party ID. So what we're going to do is we're going to create this value, and this is going to act as kind of like it's a stamp. It's going to stamp this individual signature to these parties, these nonces, and this message. We then use this row value to compute an aggregate nonce R. So we sum up the public nonces with the rows, the corresponding rows, and we add them all together. Take the first public nonce, then add that to row times the second public nonce. Add all these together, and this creates our aggregate nonce R. We also have a challenge value, which we also see in what are called sigma protocols. Sigma protocols are basic cryptographic ways of doing things. It consists with creating initial randomness, a challenge, and a response. The challenge value is going to have to depend in some way on the initial randomness, which here we have as the aggregate nonce R. So we see here the challenge is a hash of Y, which is the group public key, which is just the constant parameter of the group public polynomial, the aggregate nonce, and the message being signed. The challenge always has to depend on these things because this is what keeps you from being able to cheat the protocol. So to construct party I's signature share, Zi, we combine that party's private nonce, De, with the binding value rho, the interpolation value lambda, the challenge value C, and the secret share X, also known as the key share. So this is how we create an actual party signature share. We combine all of these things. And you'll notice before that when we were creating the aggregate nonce, we were having capital DI plus rho times capital EI. Here we're having lowercase. This means these are the private nonces, whereas that is going to have the public nonce. What's going to happen there is once we add all of these secret shares together, we're going to end up coming out with the same value. So how do we aggregate the secret shares? Well, we just add them up. Once we know our signing set, and once we get a signature share from each member of that signing set, add them all together. The full signature consists of this together with the aggregate nonce. Aggregate nonce R, which we saw how to calculate before, and Z, which we see how to calculate here above. This forms a standard Schnorr proof, and all Schnorr proofs can be verified the same way. We check that the initial commitment to randomness is the signature times G minus the challenge value times the public key. This is the way you verify all Schnorr proofs. So the question is, how does this actually give us a Schnorr proof? How does adding all these Z values together give us something that looks like this? Well, if you go back, you remember that we said that the ZI values were the private nonces plus the challenge plus the lambda plus challenge times the lambda times the private key, or times the secret share. So what that's going to do is that's going to give us, when we add together all these lambdas times secret shares times challenge values, we're going to get the challenge value times the sum of the lambdas and the secret shares. And this takes us all the way back to the Lagrange interpolation. This is how we interpolate that group private key inside here. And so since we're doing that, then we're doing the same thing you're doing in ordinary Schnorr proof, which is how we can do the same verification that we normally do. So that's it for Frost. Frost is a generic protocol which is seeing a lot of use in cryptocurrency contests, especially because it can be trivially aggregated. It has all these nice features. It can even be validated on Bitcoin as of the Taproot upgrade. But I'm not really working directly on Frost. What I've been working on for the last 2 years is what we call now WSTS. It's an optimization of Frost for the weighted threshold scenario. What weighted threshold scenario means is, well, let's think about a cryptocurrency context where you have a proof of stake or a proof of execution, proof of burn. For stacks, for example, we have 4,000 reward slots, and these reward slots are distributed based on how much an individual has stacked their stacks. So if we want to have some sort of signing mechanism, it makes sense to say that the people who have staked the most in the cryptocurrency should be able to have the most signing weight for making signatures. We'll be using this for Nakamoto and for SBTC as well. So what's the difference between Frost and WSTS? Well, in Frost, parties have one polynomial and control one secret share or one key share. In WSTS, though, parties still have one polynomial, but they control multiple secret shares. This means that the number of secret shares can be larger than the number of parties. And in fact, we do see this in stacks where we have a much smaller number of people who receive reward shares than we see have number of reward shares. So could we just use regular Frost for this? Well, we could. We could just say that everyone who gets a reward share gets a Frost party. And in fact, if we go into the WSTS repo, we'll see that this is in fact what we do for version 1 of WSTS. It's just Frost, where we just give all individual signers control over a number of parties. But the real magic in WSTS is, well, wouldn't it be better if we didn't have to repeat all these polynomials? If we could save ourselves on network bandwidth, if we could save ourselves in evaluating these polynomials. It turns out that evaluating these polynomials, when we're checking our received key shares and when we're checking our signature shares, this is actually the biggest runtime cost of any kind of Frost kind of application. And also there's a much larger number of network uses, bandwidth, latency, all of these things. So it would be better for WSTS, and we do this in the V2 version of it, to have just one polynomial that controls multiple secret shares. This allows us to have order of magnitude reductions, both in the network bandwidth used, in the latency cost, and the execution time. And this is what I've been working on for the last 2 years. And here's our references, the Frost paper and the WSTS paper. That's it for me. Thank you very much, everyone.